Hi Bobcats! In this video we are going to continue connecting gas laws to things we've learned earlier, which in this case will be stoichiometry. So we are going to see how we are going to combine these gas law calculations with the stoichiometry that we learned in a previous chapter. Now I know at this point some of y'all are saying, well, wait a minute, we already did this because the radiation sign tells us that the volume of 1 mole of any gas is 22.4 liters. But the problem with that is that that number is only good when we are at STP. If we are at any other temperature or pressure, we have to use that additional data and the ideal gas law to connect the volume of the gas. When we're connecting stoichiometry and gas laws, we need to find some sort of a game plan for relating these two different chemistry tools that we've developed already. So most of the time, the gas side of it will involve the ideal gas law, PV equals nRT. When we're doing stoichiometry, we need two numbers because we'll be talking about two different chemicals. And so one of those numbers is the coefficient from the balanced equation, which tells us the number of moles of something that's reacting. And then the other number will come off of the radiation sign, and it very well might be the 1 mole quantity. Well, what I'm trying to show is the connection between these two things is moles. Very often when we do these problems, you're going to be looking at the N from PV equals nRT, and in the stoichiometry part, you may start or end with the amount of a chemical in moles. So here's our overall game plan. It's all about moles. The moles of a gas will connect the gas laws and our reaction stoichiometry calculation. So here's our first example. How many moles of mercury 2 oxide must be thermally decomposed to produce 2.26 liters of oxygen gas at 1 atmosphere and 23 degrees C? If we were doing this face-to-face, I'd take a moment to review nomenclature and writing and balancing equations. That Roman numeral 2 in mercury 2 oxide tells us that the charge on mercury is a +2. Oxide has a -2 charge, so when we write mercury oxide, we just need 1 mercury and 1 oxygen because the +2 and -2 cancel out, giving us HgO. I'm just going to cut to the chase here and take a look at that equation. 2HgO solid yields 2Hg liquid plus O2 gas. Mercury is one of the couple of elements that naturally exist as a liquid, so that's kind of a little unusual. Okay, so there is our balanced equation. Now, we're asked to produce 2.26 liters of oxygen gas at 1 atmosphere and 22 degrees C. That's really close to STP, but not quite. So the first thing that we need to do is, since we are given data about oxygen in terms of the gas laws and asked to find something about mercury 2 oxide, we need to use that gas law data for oxygen to figure out how many moles of oxygen are present. Once we know how many moles of oxygen we have, it's a stoichiometry calculation to figure out how many moles of mercury 2 oxide are necessary. So let's do the gas law part of this. From the ideal gas law, the number of moles is equal to the pressure times the volume divided by R and T. So the pressure is 1 atmosphere, the volume is 2.26 liters, R is 0.0821 liter atmospheres per mole in Kelvin, and the temperature was 23 degrees C, which will be 296 Kelvin, because that always has to be in Kelvin. So notice that all of our units are okay. We have liters canceling with liters, atmospheres cancel with atmospheres, kelvins cancel with kelvins, and then in the denominator we have 1 over moles. So when you invert and multiply, we're going to end up with just plain old moles for our unit. Running this through my calculator, I'm going to have 2.26 divided by 0.0821, and then I've got a second number in the denominator, so I'm going to hit divide again because I don't use parentheses, and that's going to give me a value of, let's see, 0.0930, keeping 3 significant figures. And again, the units on that were moles. And this was all information provided to us about the oxygen gas. So now that we know how many moles of oxygen are involved, we can do stoichiometry to figure out how many moles of mercury oxide are needed. So let's pull that up right here. We'll have 0.0930 moles of oxygen. And I want to convert with this conversion factor from moles of oxygen to moles of mercury oxide. Now, since I have 2 different chemicals here, oxygen and mercury oxide, I've got to write 2 different numbers in front of each. The first comes from the radiation sign. On the radiation sign, the number with moles is 1. That's the same top and bottom. The second number is the coefficient from the balanced equation. For mercury oxide, that's a 2, and for oxygen gas, that's a 1. So basically, I'm going to take the number of moles of oxygen and multiply that by 2, and that's going to give me a final answer of 0.186 moles of mercury oxide. In this next example, I'm given the mass of one of the reactants, hydrogen gas, and asked to find what the volume of ammonia produced would be at 555 Kelvin and 1.77 atmospheres. That's way different than STP. There's no way we can use that 22.4 liter factor in this problem because it's so far away. So the first thing we need to do is convert that kilograms of hydrogen gas to moles, then do our reaction stoichiometry to, or convert that kilograms to grams of hydrogen gas, then do reaction stoichiometry to go from hydrogen gas to moles of ammonia. And once we know the moles of ammonia, we can use the ideal gas law to figure out what volume would be occupied. So that 1.5 kilograms is the same thing as 1,500 grams of hydrogen gas. So 1,500 grams of H2. Now I want to do reaction stoichiometry to convert those grams of hydrogen to moles of ammonia. Once we get that answer, that's when the ideal gas law will come into play. Since I have 2 different chemicals, hydrogen and ammonia, I need to put 2 different numbers in here. The first number comes off the radiation sign. For moles, that number is 1. For grams, that number is the molar mass. For a single hydrogen, it would be 1.01, but we have 2 of them, so that'll be 2.02. The second number I need to put in this conversion factor is the coefficient from the balanced equation. For ammonia, that's 2, and for hydrogen, that's a 3. So now I'm ready to run those numbers through my calculator. I have 1,500 times 2 divided by 3 and divided by 2.02. And that's going to give me, let's see, 495 moles of ammonia. And now I can use the ideal gas law, which, rearranging it a little bit, tells me that the volume is equal to nRT over P. And so the number of moles of ammonia was 495. R is 0.0821. T is 555 Kelvin. And P is 1.77 atmospheres. To try to save a little space, I didn't write all of those units, so it is really important that you double check all of the units are correct. And then if I run this in my calculator, I've got 495 times 0.0821 times 555 divided by 1.77. And that gives me a really big volume, but that's a lot of stuff reacting. I'm going to have 12,744. The answer is going to be in liters. Looks like I can keep about 3 significant figures, so that's going to be about 12,700 liters. Our goal for this video was to combine gas law calculations with stoichiometry. The key to doing this successfully is moles. We'll do moles at some point in the calculation with stoichiometry, and then we'll use moles with the ideal gas law to find whatever we need.